Hi guys, in this lecture what we will do is, we will take a look at different kind of problems that can be asked in GATE examination from machines, transformers. So the basic aim of this lecture is to provide you an insight into what kind of questions can be asked and how to deal with such kind of problems. These problems have been collected from various sources and they need not be unique. They are just to give you an insight or illustrate the problem solving procedure. Okay? So I'll give you a certain basic concepts while going through the problems that are required for solving that kind of problem. So let us get started with the first kind of problem that can be asked is dimensions of a transformer. So what such kind of problem involves is if we scale the transformer, if we change the dimension of a transformer, what is the effect on different parameters? So remember, whenever we scale a transformer, you have to keep electric field and magnetic flux density constant. These two things are always constant. So what happens is we scale all the dimensions in a similar ratio. That is, suppose length will be made 2L, width will be made 2W, and height will be made 2H. So all will be scaled by the same factor. Now what is the effect on different parameters? The first one is no load current. I naught, which comprises of I mu and IW, both are scaled by a same factor x. That is the factor by which the dimension is being changed. That is why I naught will also be scaled by the same factor x. What about now core loss? It will be scaled by a factor of x cube, that is proportional to volume. Okay, because if length is doubled, width is doubled, height is doubled, the core loss will become 8 times. Current rating, it will be scaled by a factor of x square. So if length is doubled, it will become 4 times. Rated voltage, it will also be scaled by a factor of x square. kVA rating, it is basically product of voltage and current. It will be scaled by a factor of x4. Okay. So that is how different parameters are scaled whenever we change the dimension of a transformer. Now let us take a look at the problem that is given. Two transformers of same type using the same grade of iron and conductor are designed to work at the same flux and current density. Okay, that is what I was telling you. But linear dimension of one are twice that of other. Determine the ratio of kVA rating, no load, current and the core losses. So we know that dimension of the second one is equal to 2 times the dimension of first one, which means kVA of second one, it is proportional to x to the power 4, 16 times kVA of first one. Similarly, no load current, it is simply x times. Then core losses, it is x cube, that is 8. Okay. So that is how your kVA rating, no load current and the core losses will change. So this thing you have to keep in mind. Moving on to the next problem. The next problem is based on induced EMF in a transformer. So what is the problem in such kind of questions is we often get stuck determining what will be the polarity of induced EMF. We already know that whenever we want to find the induced EMF, we have to use the Faraday's law or the Lenz law. We know in case of Lenz law it is induced EMF minus n d phi by dt. So what I will suggest is you do not have to use this minus sign. Why? What you should do is you should first figure out the polarity of induced EMF and then just calculate the magnitude using n d phi by dt. No need to consider the negative sign. Now how to find the polarity of induced EMF? For that we use the method of dot convention. Now how do we use the method of dot convention? First of all, as you can see in this problem, we have to find the polarity of induced EMF on the secondary. Induced EMF on primary is shown. So assume that the current enters in the primary positive. Why I am assuming this? Because primary winding absorbs power from the supply. So current always has to enter the positive terminal on the primary. Now place a dot here. Okay. Now what to do is, based on the current direction, determine the direction of flux. As you can see, the current is clockwise, the flux will be upwards. So the flux will be like this. Okay. Now in the secondary winding, for dot convention, in the secondary winding, the current must flow in a manner that it aids the primary flux, or it gets added to the primary flux. Now this statement might seem contradictory to many of you based on transformer principle, but this is just for dot convention. So keep this in mind, the secondary flux must get added with primary flux to place the dot. It has nothing to do with transformer, it is just a concept of magnetically coupled circuits. Now where should the current enter? For the flux to be downwards in this branch, why? Because primary flux is downwards. So secondary should also be downwards in order to get added. What should be the direction of current? The current should be such that it leaves from here and enters from here. In that case, the current will flow like this and the flux will be downwards. Okay. Now wherever the current is entering, you have to place the second dot there. Now once we have got the dot, here as you can see the dot is positive, so here also the dot will be positive. So now we have figured out the polarity of induced EMF in the secondary winding. Let us take the next example. I will again do the same procedure. Entering current I will place a dot here. The flux will again be clockwise. Now secondary flux should again be downwards in order to add up to the primary flux. If such thing happens, the current must be like this, so that the flux is downwards. Okay. So that means the dot will come here, here, and since the dot on the primary is positive, this will also be positive, this will be negative. Okay. In the next problem, again assume current I enters here, place a dot here. Now since current I is entering here, the current will flow like this. Since current is flowing like this, the flux will be downwards, or you can say anti-clockwise. That means in the secondary winding, the flux is upwards. So the secondary flux should also be in the same direction. If secondary flux is in the same direction, the current must flow like this, so that secondary flux is also upwards. That is, the current must enter here. If current enters here, this will be the dotted terminal. Since dot here is positive, the dot will be positive, plus, minus. Is it fine? In the next one, again assume that the current enters here. I will place the dot here. By taking the direction of current and using right hand thumb rule, I can see that the flux will be downwards, or it will be anti-clockwise. Once I have established this, the secondary flux should also be like this only, that is anti-clockwise. That is, in secondary winding, the flux must be upwards. For that, the current must be, how the current should flow? The current must leave here and enter here. If current enters here, the flux will be upwards. Since the current is entering at the D terminal, I will place dot here. Dot is positive, the dot will be positive, plus, minus. Once you have identified the polarity of the induced EMF, then you will simply apply N d phi by dt to calculate the magnitude. Since you know both magnitude and the direction, you can write the final answer. So if I would have asked you what is ECD, as you can see ECD is negative in the first and the fourth case, so you will keep minus n d phi by dt in the second and the fourth case, sorry, first and the fourth case. If I would have asked ECD in the second and the third case, as you can see C is positive, D is negative, so ECD will be positive, that is n d phi by dt in the second and third case. So that is what I am telling you, derive the direction and then find the magnitude. In the next problem it is saying ABC are the three windings of a transformer having 200, 100 and 60 turns. Now 100 volt is applied across A. Find the voltage developed across X and Y. For that to happen, again I will have to use the dot convention. So I will assume this as the dot. Current is entering here. So the flux will be clockwise. Since the flux is clockwise, the flux in secondary should also be clockwise. That is, in the B, it must be clockwise or it must be downwards. If it is downwards, then how the current should flow? The current should enter in the X terminal like this. So I will place the dot at X. Similarly, the current in the C should be such that the flux is towards the left, that is adding with the primary flux. So how the current should enter? It should enter Y. So I will place a dot here. Now we know by the transformer principle, V2 by V1 is equal to N2 by N1, which means the voltage across B is 100 into 100 by 200, that is 50 volt. Similarly, voltage across C 100 into 60 by 200, that is 30 volt. Now what is meant by VB? VB means that the X terminal should be positive and this must be negative. Similarly, VC, Y is positive and this one is negative. Now if you want to find out VXY, it will be VB minus VCY. Here we will go plus to minus, then minus to plus. So both are opposite polarity. So VB minus VC, that is 50 minus 30 equal to 20 volt. Okay. If it was plus minus, then plus minus plus minus, we will have added both the EMF. So you will add or subtract the individual EMF based on their polarity. Polarity can be found out using the dot convention. Moving on to the next kind of problem that can be asked in induced EMF. Here I have given you a transformer in which primary turns are 200 and secondary are 500. We want to find out induced EMF in both the windings. Now as you can see, current is shown here, dot is also placed, here also dot is given. So if PQ, if you see, primary must absorb power, so PQ must be like this. Current must enter the positive terminal. Similarly, secondary must deliver power, so current should leave the positive terminal. Which means the polarity that I have given you in the primary is wrong. The plus terminal should be upper one and the negative should be lower one, which means the polarity is negative, or I can say EPQ will be minus N1 d phi by dt. But in the secondary, the plus minus that have been shown are same as they should be. So ERS will be N2 d phi by dt. Now before moving further, we have to find d phi by dt. Flux graph is given here. So what will be the slope here? 0.009 by 0.06. 0.9 by 6, 0.15. Slope here is 0. Slope here is 0.009 by 0.02. 0.9 by 2, that is 0.45. That is also minus sign because it is decreasing. Now in order to find the voltage, you just have to multiply it by number of turns. So first if we plot ERS, you will multiply it by 500 turns. So 500 into 0.15, how much will it be? 5 into 15, that is 75. Then it will go to 0 for some duration. Then it will be minus 225. What about EPQ? In EPQ, you will have to multiply by 200. But remember, there is a minus sign also. 200 into 0.15, that is equal to 30. But with a minus sign, it will be minus 30. Then it will go to 0. Then minus 0.45 into 200, minus 90. But due to a minus sign, it will be plus 90. So that is how you can calculate the induced EMF in primary and secondary. So first figure out the terminals, then apply n d phi by dt. Moving on to the next category of problem, that is based on equivalent circuit of transformer. Now we know in case of equivalent circuit, what is the circuit? Primary resistance and reactance, core loss resistance, magnetizing reactance, secondary resistance and reactance. R1, X1, RC, XM, R2, X2. Now, in this certain points you have to remember that the no load current is equal to I mu plus IC, or sometimes we call it as IW. That is, the core loss current and the magnetizing current will total up to the no load current. Okay. And when you are adding these, add these as phasors because they will be 90-degree phase shifted. Why? Because one is the current in a resistor, other is in a inductor. Now let us see what kind of problem can be asked based on equivalent circuit. See, here it is saying it is an ideal 3-winding transformer. What is meant by 3-winding? That there is one primary and the two are secondary and tertiary. The turns ratio is given to us. N1 is to N2 is to N3. That is 4 is to 2 is to 1. Now a resistance of 10 ohm is connected across winding 2 and capacitor of reactance 2.5 ohm is connected across winding 3. We know the voltage phasor, we need to find the current phasor I1. Now the best way to solve such kind of problem is refer the circuit to one side, that is your primary. For referring, we know while referring any impedance, we have to multiply it by the turns ratio square. So what will be the resistance in winding 1? 10 ohm into N1 by N2 whole square, which is 10 into 4 by 2 square, or we can say 40 ohm. Okay. Similarly, what about reactance in 1 for the primary winding? It is minus J 2.5 into N1 by N3 whole square, that is minus J 40 ohm. Now as you can see, these impedances are connected across the winding in secondary and tertiary. So in primary also they will be connected in parallel to the winding. So what will be the circuit? This is the supply. A resistance and a reactance are connected across the supply. 40 minus J40. This is 400. So what will be the current I1? I1 will be sum of the current in each one. 400 angle 0 by 40 plus 400 angle 0 by minus J40. That is 10 plus J10. That will be the current phasor I1. Okay. So the critical point in such kind of problems is determining the connection of individual impedances when they are referred to primary. So see their orientation with respect to winding. Are they connected in series with the winding or parallel to the winding? If they are in parallel to the winding, while referring also they will be parallel. If they are in series, they will be in series. Moving to the next problem. It is saying consider the circuit shown below if ideal source supply is 1000 watt, half of which is delivered to 100 ohm load. What is the value of B? Now it is giving us the supply power. Okay. And it is saying the 100 ohm absorbs half of this, that is 500 watt. Which means other half is absorbed by 4 ohm and 25 ohm resistances. Now it is asking us the value of B. Now one thing, if you see here, these transformers are ideal, which means their resistance and reactances are 0. Now in the entire circuit only resistances are used, which means this circuit has unity power factor, which means the power input will be Vrms Irms, as the cos phi will be 1. It is giving it to us as 1000. So 100 into primary current is 1000, which means I1 is 10 ampere. Okay. Now once I know this, what I'll do is, I know in the resistance of 100 ohm power is 500 watt. So I can calculate I3. I3 will be 500 by 100 under root, that is under root 5 ampere. Based on that I can calculate I2 just by turns ratio. I2 will be B under root 5 ampere. And from first if I calculate, I2 will be, or let us calculate I1. I1 will be AB under root 5, which is already equal to 10, which means AB will be equal to 10 by root 5. So that is the first equation that I get. Once I know this, I need to find another equation because there are two variables A and B. So what I do is, I know half of the power is consumed by 100 ohm, which means the other half is consumed by the two resistance 4 ohm and 25 ohm, which means 500 will be equal to I1 square 4 plus I2 square into 25. What is I1 square into 4? I1 was AB into root 5, A square B square into 20. I2 was B root 5, which means 5 into B square into 25. That is 500. Now what I can do is, I can keep A square is how much? 100 by 5 B square. How I am writing this? I am writing this from this equation. So 500 will be how much? 400 plus 125 B square, which means B square is 100 by 125, 25 4 5, which means B is 2 by root 5. So that is how you can calculate the B. The other method to solve a similar kind of problem is referring the entire circuit again to primary and then solving it. After that, what you can do is, you can apply the maximum power transfer theorem, because we know in maximum power transfer half of the supply power is transferred to the load, which is the case here. So here you can also apply maximum power transfer theorem. Moving forward, in equivalent circuit in recent years it has been seen a different kind of problem. What is the problem here is, based on the self and the mutual inductances rather than reactances, here inductances are given. We have to find the leakage and the magnetizing inductance. So for that, what you have to remember is, suppose self primary is LP, self secondary is LS. Self secondary means self inductance of secondary winding. Mutual is, let us say, M. So what is leakage inductance in primary? That will be LP minus M N1 by N2. What is leakage in secondary? Ls minus M N2 by N1. What about magnetizing inductance? Since magnetizing is always connected in primary, M into N1 by N2. Now one thing that I have assumed here is this inductance has been measured on the secondary side. This has been measured on primary side. That is why I do not have to refer any inductance to any side. It is already referred. Is it fine? Otherwise, for referring the self-inductance, you have to use turns ratio square. For referring mutual, you have to use the turns ratio. That is the rule that you have to use. Now let us see how does this apply in this problem. It is saying the parameters of for a 220 by 110 volt 50 hertz single phase transformer. V1 by V2 is 220 by 110, which is 2, which is also equal to N1 by N2 because it is single phase. Now self-inductance of primary winding is 45 millihenry. Then self-inductance of secondary, it is 30 millihenry. Then mutual is 20 millihenry. What about leakage inductance of primary? Self-inductance minus N1 by N2 into M, that is 2 into M, which is 5 millihenry. What about leakage inductance of secondary? Now here we have to refer all these parameters on the primary side, but let us anyways calculate LLS 30 minus N2 by N1, that is 20 by 2. That is how much? It will be 20 millihenry. But this will be on the secondary side. We have to refer it to primary. So when you refer it to primary, 20 into N1 by N2 square, that is 2 square, that is 80 millihenry. What about mutual or magnetizing inductance? That is N1 by N2 into M, 20 into 2, that is 40 millihenry. So that is how you deal with the inductances in a transformer. The next concept is testing of a transformer. So there are two types of tests. One is the short circuit test. Other one is the open circuit test. In short circuit test, it will always be conducted on the HV side. Why? Because rated current is small. Open circuit test is conducted on LV side. Why? Because the rated voltage is less. So open circuit test is conducted at rated voltage and the short circuit test at rated current. Now in short circuit test, we want to determine the parameters of the series branch of transformer. In open circuit test, we want to find out the parameters of shunt branch. So in this question, what it is asking us is, we need to find the power factor of the transformer if it is operating at maximum voltage regulation. Now for maximum VR, we know cos of phi will be R by Z. That is for the series branch, which means I have to utilize the data of the short circuit test. What is given in short circuit test? Voltage, current and real power. Now if you divide voltage by current, what we will get is impedance. So 104 by 8, we get a 13 ohm impedance. If we divide power by I square, because we know the real power can only be consumed in a resistor. So it will be 320 by 64, 5 ohm. That is our resistor. What about reactance? Under root Z square minus R square, that is 12 ohm. But power factor will be simply 5 by 13, that is R by Z. Okay. If it were asking us about the no load losses, core losses, then we would have gone for the open circuit test. So remember, The open circuit test tells about the core losses, whereas the short circuit test tells about the copper loss. Is it fine? Moving on to the next type of problem that can be asked is losses and efficiency. Now what happens is, what kind of losses are there in a transformer? There are first one called as iron loss, which is hysteresis plus eddy current. Now hysteresis loss is equal to Kh Bm to the power 1.6 F into volume. Whereas the eddy current loss is Ke Bm square F square. Okay. Now this F is basically frequency, Bm is the maximum value of magnetic flux density. Then we have copper loss. Copper loss are basically I square R loss. Other than that, there are two losses, dielectric loss and the stray load loss, which are usually neglected for computational purpose. Now what you have to remember is Bm is proportional to V by F. Okay, voltage upon frequency. So if V by F is constant, Bm is also constant, which means hysteresis loss is proportional to frequency and eddy current loss is proportional to frequency square. Now let us see what kind of problem can be framed on these losses. It is saying a 400 by 50 Hertz transformer, the total core loss is 2400 watt. Okay. Now when it is supplied at 200 volt 25 Hertz, core loss is 800. Now whenever we are talking about core loss, first calculate V by F. Initially it is 400 by 50, that is 8. Then 200 by 25, that is again 8. Since V by F is constant, hysteresis loss is Kh into F, eddy current loss is Ke into F square. Now we have to find the hysteresis and eddy current loss at initial condition 400 volt 50 Hertz. Now as you can see, the frequency is halved while going from 50 to 25, which means the new hysteresis loss will be half and frequency is halved, so eddy current loss will be becoming 1 by 4. It is proportional to frequency square, which means initially the sum of hysteresis and eddy current was 2400. Now hysteresis loss is halved and eddy current 1 by 4, it is 800. If you solve these two equations, you get hysteresis loss at 800 watt and eddy current as 1600. That is your option D. Is it fine? Similarly, what I suggested you can be applied to the next set of problem. That is, I told you, if V by F is constant, hysteresis loss is proportional to frequency and eddy current to frequency square. If you divide iron loss by F, you will get Kh plus Ke into F, which is the equation of a straight line with intercept equal to Kh and slope will be equal to Ke. Now if you see from this graph, what it is saying, an open circuit test is performed. Why open circuit test? Because we are determining core losses using variable frequency source, keeping V by F constant to separate eddy current and hysteresis loss. The variation of core loss upon frequency, that is Pi by F versus frequency, is shown. So the intercept basically Kh is 10 and the slope is how much? This is 5, this is 50, that is 0.1. We need to find the hysteresis and eddy current loss at 25 Hertz. So pH will be Kh into F, that is 10 into 25, 250 watt. Then eddy current 0.1 into 25 square, that is 62.5 watt. So that is one other method of determining the hysteresis and eddy current loss. Moving to the next one. A 20 kVA 220 by 110 volt 50 Hz single phase transformer has full load copper loss 200 watt, core loss 112.5 watt. At what kVA the load and the power factor should be transformer be operated for maximum efficiency? For maximum efficiency, the condition in any machine is that the constant loss should be equal to variable loss. In case of transformer, the constant is core loss, which must be equal to copper loss. Or we can say this is equal to x square PCU FL. Why x square? Because if current becomes x times IFL, copper loss is proportional to current square, I square R, copper loss will become x square, which means x P core by PCU FL. What is the x here? X is the fraction of full load. That is, if I am operating at half load, x will be half. If I am operating at quarter load, it will be 1 by 4. So it represents the load at which you are operating as a fraction of full load. Okay. At half load, it is half, quarter load 1 by 4, 1/3 load, it will be 1 by 3. So for maximum efficiency, x must be this. In our case, it will be 112.5 by 200, which is 0.75. That is, you have to operate at 75% of the full load in order to obtain maximum efficiency. What about power factor? Remember, power factor must always be unity for maximum efficiency. That is, entire power must be real power. Now, what about maximum efficiency? It is, let me first write down the formula for efficiency. Always remember, eta is x into kVA cos phi. X is the fraction of load, kVA is the kVA rating. X kVA cos phi Pi plus PCU. PCU is also written as x square PCU full load. Now for maximum efficiency, we know iron loss and core loss are equal. So x kVA cos phi by x kVA cos phi plus 2 times the iron loss. 0.75 we have derived, kVA is 20, cos phi is 1. 0.75 into 20 into 1 plus 2 times the iron loss, that is 225, but we will divide it by 1000 because we are taking in kVA. So this will approximately come out to be 97%. So that is the maximum efficiency, and always remember, transformer is a kind of machine which always operates at a very high efficiency. So such kind of problems can be framed from transformers. In the next lecture, what we will do is, we will look at other type of problems that can be framed in the transformers.